All right, chapter 6.2, we're going to be finding volumes of rotated solids, and just to give you an idea of that you have some graph, whatever it does, let's say it does something weird like that, and it creates some region here, like so. And we take that region and we rotate the axis. So you imagine that that's got paint or something on it, and you rotate that picture around. It's going to create a three-dimensional picture. That's not very good, but that would kind of make a bell, right? Imagine that. So, you know, if you kind of imagine this circular shape here, that's kind of what's happening there. So we have that object gets rotated around, and that object has some sort of a volume. Okay, and the idea, what we're going to be doing today, is imagine if we slice this into a bunch of circles, right? So you slice it here and here and here, and you just make a whole bunch of cuts along that. Each one of those circles has some area, right? You take the area of that region, it's going to be some function of x, and you integrate that from the beginning to the end. And that's what the volume equals. So we find the area of the circular cross-section, and we simply find the integral of the circular cross-section's area from the beginning to the end of the interval in terms of x, and we get ourselves a volume. All right? And the basic process here, if you go step by step through it, step one, you want to graph the region. Right? Just graph it, actually put it on paper and shade it. And just use your pencil, just a really light shade, just to identify this is my main region. It gets more important to do that as we get to the problems where they're not going around the x, y axis, where they're up above or down below or off to the right or left. You rotate, and the way you rotate, just draw, you know, basically, you got your regular graph, and then you draw the reflection of that, and then you put like some ovals in it, that shows the rotation. And you want to draw circular concentric circles to represent a cross section. The reason I say concentric circles, sometimes there's holes in the graph, and if there's holes in the graph, then you'll get like a circle and then a circle on the inside. So concentric, that means two circles have the same center. They look like this. It's like a washer. Anybody works with hardware, one of those flat washers, right? Once you've drawn that circle, you want to determine the radius or radii, if there's more than one circle, in terms of x. So again, this is assuming a rotation like this. We want everything in terms of x. All right? If it's a rotation like this, we want the radius in terms of y. All right, well, that's what this talks about here. Change x to y. Right. Find the area of that circular cross-section. What's the area of a circle? Pi r squared. So whatever the radius is, if the radius is x, pi x squared is the area of the circle. If the radius is 1 minus x, the area is pi times 1 minus x, quantity squared. Simplify, then you work it out. And then integrate, and then you're done. Okay, so it's a pretty straightforward formula process. It does require a little bit of graphing, and I don't know, just some people get hung up on the artwork here. You don't have to be an artist to do this. Just, you know, draw the picture the best you can. What you need to do is be able to get this circle and figure out the radius. You need your drawing to be good enough to be able to do that. Everything else is pretty much just applying a little bit of calculus to it. So, look at example 1. Find the volume of the solid obtained by rotating about the x-axis region under the curve y equals the square root of x from 0 to 1. All right. Anytime it says from something to something, that's from x equals those numbers. All right. So, you can see here I've used a 0.25 scale on both the x and y axis. That's usually a decision you make after you get a table made. I've got preconceived knowledge about this one, so I went ahead and put that on there. You never want your graph to be so tiny you can't do anything with it. So if you have a 1 scale here, we're going from x equals 0 to x equals 1. Square root of 0 is 0, square root of 1 is 1. The graph would be that. You can't do much with that. So again, by shrinking the interval, making these smaller, it allows us to expand the size of the graph, giving us room to write. So, if I just did this, the square root of 0 is 0, the square root of 1 is 1. Those 2 points are easy. Anybody know the square root of 0.25? 0.5. Square root of 5. 0.7071. Square root of 0.75. 0.8660. You don't have to know those numbers. You can always just use a calculator. Y equals square root of x. Go to your table. 0.0, 0.25, 0.5, 0.751. So just for the sake of saving a little time, I'd have to know those. So there you go. That's what y equals the square root of x looks like. Now, every region that you're going to get is assumed to go down to the x-axis. Unless there's, it says region under the curve, it means to the x-axis. If it says region bounded by, then you're going to be between two curves. Okay, so if it says region bounded by curve 1 and curve 2, and they do something like that, that's my region. All right, that could happen. But if it says under the curve, they simply mean under the curve till you hit the x-axis and you stop. So my ending point is here. So I'm starting at 0, I'm on the x-axis. I'm ending at 1, which is above the x-axis, so I draw a line down to the x-axis. And then I'm going to shade that in. And again, you're doing it with a pencil. Just do a real light shading on your pencil. You don't get real dark there. You want to be able to read things that are happening inside of there. I've got a highlighter so I can do this. But you do want to shade that area. That's my original region. That's what step 1 is in the process. Step 2, we're going to rotate it. And it does say rotation about the x-axis. So they always have an axis of rotation. This is the axis of rotation. The axis of rotation will be either a horizontal or vertical line. Today it's going to be the x-axis. Tuesday when we revisit this, it's going to be the y-axis. And then Wednesday it's going to be like x equals 1 or y equals -2. It'll be a horizontal or vertical line, not on an axis. All right, and that creates some issues of their own. But that region is being rotated this way around the x-axis. So its reflection is there. And if you just imagine kind of an oval there, just to give it a little bit of depth, so we can kind of see in there. All right. And what I want you guys to imagine here is this, that shape there, again, is a rotational shape. So the x-axis is the radius, right? Or the center, and then we're going some different distance here. And each of these circles that are being created, because we're rotating around the axis, we're not changing. So if I'm at this point here, and I go on a right around the axis, I'm going to create a circle, right? And if I'm at this point here, same deal, and so on. So every one of those points, and I've got the points I've actually marked, but there's the infinity points along there, create circles, right? So if I just pick any one of those circles, doesn't matter where I put it, I'm going to take that one right there. And I imagine a radius on that circle. I want to take that circle out of the picture, and we want to identify its radius. So let me just put a dot here. There we go. And draw my circle. There we go. That is that circle right there. Now, it's very important that the radius is the distance from the x-axis to the curve itself. And the radius, if I'm going up and down, is equal to y. So the radius is equal to y. Is the radius the same for all the circles? No. So if I'm here at something, if I'm here at something, if I'm here it's 0.5, if I'm here it's 0.7071, if I'm here it's 0.8660, if I'm here it's 1, it's changing. Okay? But every time I look at what the radius length is, it goes from the x-axis up to the curve, which is a height of y. Right? If you look in step number 4, determine the radius in terms of x. All right? So the first thing you do is just establish that it is y. All right? And if we're going this way, the radius will be x. All right? It'll be either x or y right now. All right? So the radius is y, but y equals the square root of x. That's what you want to put in your circle. And again, for now, that's what the radius will be. It'll either be x if it's a rotation like this. It'll be a y if it's a rotation like that. When we start moving up and down and left and right, then it's going to be something else. But right now, it's going to be either x or y. Whatever the radius is, you want to put it in terms of the other letter. So if I'm doing this rotation, I want everything in terms of x. Easy to get the radius in terms of y, but then you've got to change it using the equation. Right? Once I get the circle figured out with the radius figured out in terms of x, I simply have to apply the area formula of the circle, which is area is equal to pi times the radius squared. So the area of that circle is simply going to be pi x. Whatever you get for the area formula for that circle, the volume is equal to the integral of that formula dx. And we're going to integrate from the starting point x equals 0 to the ending point x equals 1. Our circles start at 0, they end at 1. That's what we're integrating. That's how we create our formula. Then we simply have to evaluate that integral. Pi is a number, right? Numbers can be pulled out of integrals. So if you even want to do this, pull that pi out in front. The area formula always has a pi on it because it's always going to be a circle, right? That pi can always be pulled out in the front. So if I integrate this thing, the integral of x is x squared over 2. So pi x squared over 2. If I put 1 in, I'm going to get 1 over 2 times pi, so that's pi over 2. If I put 0 in, I'm going to get 0. So the volume of that shape is going to be pi over 2 cubic units.